Please welcome to the stage Dr. Zdenka Kuncic, Professor of Physics at the University of Sydney.
So, the origin of artificial intelligence can be traced back to British mathematician Alan Turing, who in 1948 asked the question, can machines be intelligent? Now, he outlined a couple of really interesting ideas for computing machines. He wrote a visionary paper in which one of the ideas of his computing machines was pretty much described as a logical computing machine, which we today recognize as modern computers, essentially. But what people know less about is the fact that he also articulated another type of computing machine. This type of computing machine was quite different from the one based on logic. It was inspired by the unorganized structure of the human brain. And so he argued in that visionary paper that a type of unorganized computing machine would exhibit a form of intelligence that would be similar to the intelligence that our brains also exhibit. So Turing's brain-inspired model can, in many respects, be regarded as the inception of what we today call artificial intelligence, or AI. Now, about 10 years later, American scientist and engineer Frank Rosenblatt actually built the first AI. It was called the Mark I perceptron. Now, no one really here who knows anything about AI would actually recognize Rosenblatt's machine, because it was actually a physical hardware machine rather than software, which is how we use AI today. So Rosenblatt's perceptron, his perceptron machine, was made up of a whole jumble of wires, as you can see in this picture, and it took up a huge amount of space. On top of that, it didn't work very well either. By the mid-1960s, the invention of semiconductor transistors miniaturized previously bulky vacuum tubes that had up until then been used in all the computers. So the invention of transistors and their subsequent implementation into computers dramatically reduced their footprint from room size to desktop size. And it also paved the way for software to program logic-based circuits. So this marked the birth of digital computing, which we all use today in our modern computers. Today's AI uses artificial neural networks. These are software algorithms that are only loosely inspired by the brain. They can achieve seemingly superhuman abilities in finding patterns in really big data, and that's what they're really, really good at. And they do that through brute force computations using specialized hardware, like GPUs, for example, that contain hundreds and hundreds, if not thousands, indeed, transistors. However, artificial neural networks also consume enormous amounts of power, and much more power than the brain's neural network. And this problem has come to the fore with the introduction of really large AI models like ChatGPT. It's been estimated that by about 2030, the massive data centers that run AI software are going to consume as much energy as a European country like Germany or France. They also consume enormous amounts of water to prevent them from overheating. This is unsustainable. So I'm going to show you how we can make machine intelligence much more efficient by creating an entirely new type of hardware architecture that's more closely aligned with Turing's original vision, and that uses technologies that were not available in Rosenblatt's day. This is nano-intelligence, machine intelligence in a nanoscale hardware architecture that mimics neural networks. Only these aren't algorithmic neural networks, they're physical neural networks. And they're orders of magnitude more efficient than what's used today in artificial neural networks. And what's more, they're based on physics principles. We use nanowires, long, tiny wires that are only a few nanometers thin. It's about 1,000 times thinner than a human hair. They naturally self-organize into an intricate network architecture. So this is very similar to a network architecture that's exhibited by biological neural networks. And importantly, they also work through electrical switch junctions, similar to transistor switches. However, they're more highly interconnected than transistors are in a typical chip. And also, they're made out of different types of materials. So whereas transistor switches are made out of semiconductor materials, these particular types of electrical switches in nanowire networks are typically made out of metal dielectric materials. Now, what this means is that they exhibit some really intriguing properties, like memory and also emergent dynamics. Whereas AI software tries to emulate brain-like computing, we get interesting brain-like properties in these nanowire networks for free. And we can actually perform some machine learning tasks. So this makes them quite different from artificial neural network software because we are actually demonstrating machine intelligence within the hardware itself. Nanowire networks contain hundreds of thousands of these electrical switches, which are known as memristors. So these are nonlinear variable resistors with memory embedded within them. These memristors form across the nanowire-nanowire intersection points. And it turns out that quantum tunneling also plays an important role in creating some really interesting emergent dynamics that enable computational abilities beyond the reach of digital logic. We found that because these memristors mediate many, many interactions between the nanowires, the networks can self-organize their dynamical state into a thermodynamically optimal state for information processing. Memristors control the physical network weights based on electrical conductance. This means that they can self-adjust their weights to changing input signals. This is something that artificial neural networks can't do. but it's something that real neural networks and neuronal synapses do incredibly well. This makes these particular physical nanowire networks orders of magnitude more efficient than artificial neural networks as well. And with artificial neural networks, what needs to be done is to train the network weights and then update them in data centers, which is very expensive. So we've created neural network devices that can be used not just for conventional machine learning, like, for example, image classification, but also to demonstrate their ability to remember and learn on the fly. For example, we've shown how they can remember a sequence of digits, like a telephone number, and also how they can recognize speech. We've discovered that these nanowire networks also exhibit a type of working memory similar to the brain, where you can remember an important piece of information while at the same time continuing to process other less important information. We've also shown how these nanowire networks can be used to predict unpredictable signals, like the classic Lorentz chaotic attractor signal shown here. Nanointelligence is the key to machine intelligence as originally envisaged by Turing himself. Thank you very much.